Hi everyone, so this is part 2 of your three-part, three-phase systems review, and today we're going to be covering phase and line voltages and their relationships in delta and star connected systems, and also we're going to look at the delta Y transformation and how to derive it. So there are two typical configurations we use in three-phase, delta and Y, as you all know. And when we use these configurations, we could change the relationship between phase voltage and line voltage. In the previous session, we looked at the changes in the Y voltages in looking at phase and line voltages, but now we're going to look at the differences between Y and delta. So for the Y configuration, we have the phase voltage here, as you could see, from the neutral point to the line, and then we have the line voltage, which is just between two lines. So we have VA, which we're going to define as VM angle 0. VB will be VM angle minus 120, and VC, which is VM angle 120. And if we want the phase voltage, the line-to-line voltage, that will be the voltage between A and B. This will simply be VA minus VB. And looking at the whole phasor, VM angle 0 minus VM angle 120, minus 120. So if we looked at our three-phase voltages, which is VA and VB, remember this would give us a vector going from B to A, which has an angle, if I draw this at the origin, has an angle of 30 degrees, and the magnitude works out to be √3 by Vm, which is the magnitude of VA. So that is what we have here, √3 Vm angle 30, and this is 30 degrees more than A. If we went from B to C, it would be 30 degrees ahead of B, and if we went from C to A, it would be 30 degrees ahead of C. So this 30-degree shift is relative to what the voltage at the first subscript is here. So if it was VBC, VB, which is minus 120, we would get 30 degrees ahead of that, which would be minus 90, which is the straight line down here. So the other thing to note here is that I phase is the same as I line, because the current I phase is the current that comes through the phases, and you could see it's just in series with I line, so it doesn't change. I line is equal to I phase, and V line to line, notice I line but V line to line, V line to line is √3 the magnitude of V phase shifted by 30 degrees. For the delta configuration now, again we have our voltages defined the same way, but this time if I look at, say, the voltage between A and B, which is from here to here, if I look at the voltage VAB, you'll see that that is the same as the voltage across one of the phases. So V line to line is equal to V phase. And if I look at I line between lines A and between phases A and B, notice now we have the phases coming, the line here joins two lines, it joins two phases. It is not like in the Y configuration where the line is tied to only one phase. Here now we have the line tied to two phases. Now in reality we will say that this is I line A, so you just call it IA. But what we have is I've denoted it here with IAL for line IL AB, because I want you to make the connection that it is IA, the current through phase A, minus the current through phase B. And again, when we substitute the values for the phasor values for IA and IB, we'll end up with √3 IM angle 30. So the exact same thing holds, except this time it's for the current. So for the delta configuration, the line-to-line voltage is equal to the phase voltage. For the Y configuration, the line current is equal to the phase current, and of course the opposite is true for the currents and voltages in the reverse setting. For the delta configuration, I line is √3 I phase shifted by 30 degrees, and for the Y configuration, I line is equal to I phase. And also important to note here, there is no ground point in the delta configuration, which is also one of the reasons why line-to-line voltages is important. For the delta configuration, there simply is no ground, so you cannot measure phase to ground voltages. Good. So let's look now at what happens when we connect delta systems to Y systems and vice versa. So first we're going to look at a simple case where we have Y and Y, so we can understand how this changes when we change one of the systems to a delta. So if I have a Y system connected to a Y system, then I would find that the voltage across here on the source side is the same as the voltage across here on the load side, as long as the system is balanced. So VA is equal to the voltage across load A, VB the voltage across load B, VC the voltage across load B. And of course VAB here is the same as VAB here because it's the same two lines. Now the currents are also the same. The current coming out of A is the same current going into the phase A. So once you have two systems, this also holds for delta connected systems, a delta and a delta. Once you have the two systems which are the same, then the load voltage and the source voltage would be the same. The load current and the source current would be the same. But when you have a change, so that we have now we have a Y source connected to a delta load, then what happens is the voltage, say here, which is the line-to-line voltage, is the same voltage that appears over the phase of the delta, because remember the line-to-line and the phase voltage for delta is the same. So in this case what you would have is that the phase voltage on the load is equal to √3 multiplied by the phase voltage on the source. So just by connecting this in a different way, you could get an increased voltage on the load components. It is not necessarily that you have to get something higher, lower or the same as you would expect from single phase systems. And the line currents as well would go and split into two phases. So just like we had before in our delta configuration, we have the line current is √3 times the phase current. So here each one of these phase currents would be 1 on √3 times the line current, and of course it would be shifted by 30 degrees. Here we are just looking at the magnitudes though. So moving on now, we're going to look at delta Y transformations. So if we look at a delta or a Y simply as a black box with three terminals coming out of it, the question is whether we could replace the three components, the three resistors or the three impedances in a Y, with a delta configuration, and the impedance looking into these points would remain the same, so that if you connect it to a source, you'll get the same voltages and the same currents. The source would not be able to tell the difference between the two sets of connections. So that is what we want to look at. So to do that, what we're going to do is, let's consider a Y circuit, and the Y circuit we're going to connect between A and B, and we're going to leave C open. And we're going to do the same thing with the delta circuit. We're going to connect between A and B, and we're going to leave C open. And what we want to do is we want to find out what do these impedances have to be such that a source connected to these points will not be able to tell the difference between these two networks. So what I want is that the impedance looking into here should be equal to the impedance looking into here. I want ZAB to be the same thing here, ZAB. So if I look at ZAB here with this open, it's just going to be ZA plus ZB. And if I look in here, what I'm going to get is ZAB in parallel with ZAC plus ZBC, which is this. ZAB in parallel with ZAC plus ZBC. And now I want to find what ZAB, AB, AC, and BC would have to be in terms of ZA, ZB, and ZC. So we're going to do some mathematics. I'm going to leave you to go through it in more detail, because it's just really manipulating the equations. And you'll see it could get a little bit, not complicated, but a little bit tedious. If we look at the other terminals, so in turn, we have ZA plus ZB, we leave ZC open. Here we leave ZB open, so we have ZA plus ZC, and here we leave ZA open, we have ZB plus ZC. If we do this in turn, we get a set of equations, and now we're going to solve for it. We have three unknowns and we have three equations, and we're going to solve for the three unknowns. So what we have here now is just some manipulations of the equations, substitutions, and at the end of it, what we should get is this. This is ZA in terms of ZAC, ZAB, and ZBC. If we have these, so these are all the delta impedances, and this is the Y impedance. So if we have the delta impedance, this is what the Y impedance would have to be. If we make the system balanced so that all the impedances are equal, then we would have Z, and let's call that Z delta squared over 3Z delta. Then that would give us 1/3 Z delta. So ZY will be equal to 1/3 Z delta. The other way we could do it is to find ZAB, AC, and BC in terms of ZA, ZB, and ZC. So this is if we want to go to the delta in terms of the Y. So it's the same process of substitution, just you do it the other way now to find ZAB, ZAC, and ZBC instead of ZA, ZB, and ZC. So you'll see for the balance system, we are able to derive this. ZY is equal to 1/3 Z delta. So we could replace the delta impedances with smaller impedances, so 1/3 smaller. And if it's in a Y configuration, an external circuit is not going to be able to tell the difference. Good. So in summary, by now you should be able to draw and explain the phase and line relationships in star and delta connected systems and derive the impedance relationships for delta and Y transformations. And as I said, I just briefly went through that because you should have done this already in 1015. If you didn't, just pull up the slides from the course shell and go back through it and try to derive it. It's there in a step-by-step manner. Next time, we're going to look at three-phase power.